Let's start with how we intuitively classify the elements around us. Most of us sort them into two simple buckets: metals and nonmetals. We make this distinction based on obvious physical traits. If it has a shiny luster, can be hammered into sheets, drawn into thin wires, or rings when you strike it, we call it a metal. But using these macro-level observations to predict how an element will actually behave is a mistake. The physical state of an element is highly conditional. While hardness and shine give us a quick profile, they only represent a surface-level facade. To define true chemical identity, we have to stress test the elements to see what they hide beneath the surface. If we rely entirely on the physical classification matrix, we immediately run into severe glitches. Elements begin acting exactly like the opposite group. Take the metals. Mercury exists as a liquid at room temperature. Gallium and cesium have melting points so low they will turn to liquid just resting on the palm of your hand. The nonmetals break the rules too. Iodine is a nonmetal, yet it possesses a distinct metallic luster. Carbon, in the form of graphite, acts as an excellent conductor of electricity. Then there are the alkali metals, like lithium, sodium, and potassium. These are metals so incredibly soft that they can be sliced clean through with a standard kitchen knife. When you map these anomalies onto this grid, the traditional framework collapses entirely. You cannot rely on physical state to definitively group the periodic table. To categorize these elements accurately and to master this topic for your exams, we have to abandon appearances. We must subject these elements to a rigorous series of chemical stress tests. We map the behavioral hierarchy of elements by exposing them to progressively harsher reagents. We begin with oxygen. When heated in air, almost all metals combine with oxygen to form basic metal oxides. This visual matrix shows our first major chemical deviation: amphoteric oxides. Metals like aluminum and zinc act as chemical chameleons. Their oxides react with both acids and bases to produce salt and water. To separate the elements further, we subject them to the water trials. Here, we use a thermal gradient, moving from cold water to superheated steam, to measure exactly how violently an element reacts. At the extreme high end of this gradient, potassium and sodium react with cold water so violently that the hydrogen gas evolved immediately catches fire. Looking at the updated temperature scale on this matrix, magnesium requires hot water to react. Drop further, and metals like aluminum, iron, and zinc will only react with steam. Finally, we find the inert anchors at the bottom: lead, copper, silver, and gold. They do not react with water at all, regardless of the temperature. The next layer of stratification is the acid trial. When a metal reacts with dilute acid, it produces a salt and evolves hydrogen gas. However, there is a common hurdle in chemical analysis: nitric acid. It is a strong oxidizing agent. When most metals react with it, the evolved hydrogen is immediately oxidized into water. As you can see in this chemical flowchart, there are exactly two exceptions that bypass this trap to successfully evolve hydrogen gas: magnesium and manganese, but only when reacting with very dilute nitric acid. Even with oxygen, water, and acid, some metals show reactivities too close to easily rank. For these, we use the displacement reactions. The logic is straightforward. If you place metal A into a salt solution of metal B, and metal A displaces B, metal A is empirically the more reactive element. These progressive stress tests strip away the physical illusions. They provide objective proof of exactly which elements dominate the others. By compiling the empirical data from the oxygen, water, acid, and displacement trials, we finally have a unified framework. This vertical list is the reactivity series, a definitive ranking of metals arranged strictly in order of their decreasing activity. Notice that hydrogen sits right in the middle of this list, despite being a nonmetal. It is included as the reactivity benchmark. Elements above it will displace hydrogen from dilute acids, while those below it will not. You will need to recall this exact order. A simple mnemonic to lock this hierarchy into memory is, "Please stop calling me a zebra. I like her calling me silver gold." Potassium, sodium, calcium, magnesium, aluminium, zinc, iron, lead, hydrogen, copper, mercury, silver, gold. The reactivity series perfectly maps how these elements will behave in a lab. But to understand exactly why this hierarchy exists in the first place, we have to zoom in to the atomic level. What physical mechanism makes sodium highly explosive, while argon remains completely inert? The difference is found in the electron configuration. Look at these Bohr models. Every chemical interaction is dictated by the population of this outermost layer, the valence shell. The primary drive is stability. Atoms try to achieve a completely filled valence shell, matching the noble gases. This defines a metal at the atomic level. Metals are electron donors. They hold surplus electrons in their valence shell, and they must lose them to become stable, positively charged cations. Conversely, nonmetals are electron acceptors. They operate with a valence deficit and must aggressively pull in external electrons to fill their shell, becoming negatively charged anions. That reactivity series we mapped earlier is simply a measure of this process. It ranks how aggressively these atoms pursue stability by shedding or accepting those valence electrons. When an aggressive electron donor meets a hungry electron acceptor, the result is highly efficient. Let's look at sodium and chlorine. As shown in this transfer diagram, sodium has one surplus electron in its M shell. Chlorine needs exactly one electron to complete its octet. Sodium transfers its electron entirely over to chlorine, leaving us with a positive sodium cation and a negative chloride anion. Because these two ions now hold opposite charges, they attract each other. This powerful electrostatic force of attraction is called an ionic bond. Ionic compounds like sodium chloride don't exist as isolated single molecules. Instead, these opposing charges lock together into massive, rigidly interlocked three-dimensional crystalline grids. This dense subatomic architecture explains the macro-level traits we observe. Those powerful electrostatic forces are precisely the reason why ionic compounds exist as hard solids and have exceptionally high melting points. An element's entire profile, whether it bends, shatters, ignores water, or detonates on contact, is entirely dictated by this subatomic engine, constantly driving toward a stable octet.